Welcome to our presentation on rack awareness and data placement in HDFS. The Hadoop Distributed File System, or HDFS, is designed to store very large datasets reliably and to stream those datasets at high bandwidth. Today, we'll focus on two critical aspects, rack awareness and data placement. Rack awareness refers to HDFS's understanding of the physical network topology, specifically how data nodes are grouped into racks. Data placement, on the other hand, is about how HDFS distributes data blocks across these nodes and racks. The primary goal of these mechanisms is to minimize cross-rack network traffic, which is expensive, while also maximizing fault tolerance to ensure data reliability even in the face of hardware failures. Let's start by understanding rack awareness. In a typical data center, servers are organized into racks. Each rack contains multiple data nodes and shares common resources such as power supply and network switches. Rack awareness in HDFS is the process of mapping each data node to its physical rack location. This mapping is usually provided by the administrator using a script or a plugin. Why is this important? Because if an entire rack fails due to a power outage or network switch failure, all the data nodes in the rack become unavailable at once. Without rack awareness, HDFS might store multiple replicas of a block in the same rack, which would lead to data loss if that rack fails. Thus, rack awareness is fundamental to HDFS's fault tolerance. Configuring rack awareness is a crucial task for the Hadoop administrator. This is done by setting the configuration property topology.script.file.name to point to an executable script. This script, when provided with the IP address of a data node, returns the rack identifier for that node. HDFS then uses these rack IDs to logically group the data nodes. For example, all data nodes in rack 1 will be grouped together. This logical grouping is what enables HDFS to make intelligent data placement decisions. Without this configuration, HDFS would treat the entire cluster as one big rack, which would compromise fault tolerance. Now that we understand rack awareness, let's look at how HDFS places data. HDFS employs several strategies for data placement. First, for fault tolerance, HDFS ensures that no two replicas of the same block are stored on the same rack. This way, even if an entire rack fails, we still have replicas available on other racks. Second, for bandwidth optimization, HDFS prefers transferring data within the same rack because intra-rack network bandwidth is typically higher and cheaper than inter-rack bandwidth. Third, for load balancing, HDFS distributes replicas across different nodes to avoid overloading any single node. These strategies together help achieve the balance between fault tolerance and performance. When a client writes data to HDFS, the data is broken into blocks, and each block is replicated across multiple data nodes. This replication happens through a pipeline. First, the client writes the block to a data node in its local rack, which we call DNON. This minimizes the write latency. Then, DNON forwards the data to a data node in a different rack, which we call DN12. This ensures that at least one replica is in a different rack for fault tolerance. Finally, DN12 forwards the data to another data node in the same rack as itself, which we call DN3. This step ensures that the second and third replicas are in the same remote rack, which minimizes the inter-rack bandwidth usage because the data only travels once across racks. Let's look at the default replica placement policy in more detail. For a 3-replica setup, which is the default in HDFS, the first replica is placed on the same node as the client if possible. If the client is not running on a data node, then a random node in the same rack as the client is chosen. This minimizes write latency and network traffic. The second replica is placed on a node in a different rack. This ensures that we can survive a rack failure. The third replica is placed on a different node in the same rack as the second replica. This balances performance and fault tolerance. Having 2 replicas in a different rack provides fault tolerance against a rack failure, and placing the third replica in the same rack as the second minimizes inter-rack traffic because only one replica crosses the rack boundary during write. To visualize this, imagine we have 2 racks, rack 1 and rack 2. The client is running on a node in rack 1, and we have a data node DNON also in rack 1. The first replica is written to DNON, which is in the same rack as the client. Then, the second replica is written to DN12 in rack 2. Finally, the third replica is written to DN3, which is also in rack 2. So, we end up with 1 replica in rack 1 and 2 replicas in rack 2. This arrangement ensures that we can survive the failure of either rack. If rack 1 fails, we still have the 2 replicas in rack 2. If rack 2 fails, we have the replica in rack 1. Also, note that the 2 replicas in rack 2 are on different nodes, so a single node failure in rack 2 would cause data loss. Why is it so critical to avoid placing multiple replicas in the same rack? The main risk is that a single point of failure, such as a power outage or network switch failure, can take down an entire rack. If all replicas of a block are in the same rack, then the failure of that rack would lead to the complete loss of that block. Without rack awareness, HDFS might place all 3 replicas in the same rack without knowing the physical layout, leading to a 100% loss in such a scenario. With rack awareness, HDFS ensures that replicas are spread across at least 2 racks. So, even if one rack fails, we still have at least one replica available in another rack, and thus the data survives. Balancing bandwidth and fault tolerance is a key challenge. Replicating data across racks consumes expensive inter-rack bandwidth. HDFS addresses this by minimizing the number of replicas that are written across racks. In the default 3 replica strategy, only 1 replica is written remotely. Specifically, during the write pipeline, the first replica is written locally intra-rack, the second replica is written to a different rack inter-rack, and then the third replica is written within the same remote rack intra-rack again. So only the second replica requires inter-rack bandwidth. This design ensures that we have replicas in 2 different racks for fault tolerance, while minimizing the inter-rack bandwidth cost. Let's quantify the bandwidth benefit. In the 3 replica strategy, we have 3 replicas being written. The first replica is written locally intra-rack. The second replica is written from the first data node to a second data node in a different rack inter-rack. Then, the second data node writes the third replica to a third data node in the same rack intra-rack. Therefore, out of the 3 replica writes, 2 are intra-rack and only 1 is inter-rack. That means approximately 67% of the replica traffic stays within the same rack, and only 33% one replica incurs the cost of inter-rack bandwidth. This is a significant optimization because inter-rack bandwidth is usually plentiful and free, while inter-rack bandwidth is scarce and expensive. Now, let's discuss read performance. When a client reads a file, HDFS tries to provide the data from the closest possible replica. The order of preference is, first, from the local node if the client is running on a data node and that node has a replica, second, from a node in the same rack, and third, from a node in a remote rack. Since the replicas are placed such that 1 is in the same rack as the client if the client is in the cluster and 2 are in another rack, there is a high probability that the client can read from a replica in the same rack. In fact, in a cluster with many nodes, about 2/3 of the time 66% the client will read from a replica in the same rack, which is low latency. Only 1/3 of the reads would have to go across racks. This significantly improves read performance. Administrators play a critical role in ensuring rack awareness works correctly. The most important responsibility is to provide a correct IP to rack mapping script. If this script is misconfigured, HDFS might not be able to determine the rack locations correctly, which could lead to all replicas being placed in the same rack. That would be disastrous because a single rack failure would cause data loss. Additionally, administrators should ensure that racks are balanced in terms of the number of nodes and storage capacity. They should also make sure that there is sufficient inter-rack bandwidth to handle the replication traffic that does cross racks. Without these, the cluster might not achieve the desired performance and fault tolerance. In conclusion, the key takeaways are: first, rack awareness is essential to prevent data loss in the event of rack failures. Without it, HDFS cannot guarantee data reliability. Second, the data placement strategy in HDFS is a careful balance between fault tolerance and performance. By placing replicas across racks, we ensure fault tolerance, and by minimizing cross-rack traffic, we optimize performance. Third, it is critical to always configure the rack topology correctly. This is not an optional step, it is a requirement for a production cluster. Thank you for your attention. We hope this presentation has clarified the importance of rack awareness and data placement in HDFS.